Hello all. Today we're just going to practice some sample Regents questions about the properties of gases. So let's start. A sample of a gas is contained in a closed rigid cylinder. According to kinetic molecular theory, what would occur when the gas inside the cylinder is heated? So I would say it's not going to be number one because the number of gas molecules doesn't change when temperature increases. However, the average velocity of the gas molecules would increase. And one of the things that you can think about here is the equation Ke is 1/2 mv squared. So the way that we can increase the kinetic energy is by increasing the average velocity. All right, number 2. Which diagram best represents a gas in a closed container? The best representation is choice 1. And the reason for that is because the particles are distant from each other. But additionally, they are filling the space of the container, so they fill the volume. Unlike this one, which some people might think is a gas, but it doesn't fill the volume. Okay, so we have a sample of oxygen gas sealed in container X and a sample of hydrogen gas sealed in container Z. Both samples have the same volume, temperature, and pressure, so which statement is true? We can use Avogadro's hypothesis here, which basically states that if you have two samples of gas at equal pressures, volumes, and temperatures, that the number of molecules are also equal. So you can see how that relates to question 3 here, because sample X and Z have the same volume, temperature, and pressure right here. So that means they must also have the same number of molecules. And lastly, on this page, a sample of helium gas has a volume of 900. That's going to be our V1 milliliters and a pressure of 2.5 atmospheres. So that's my value for P1 at 298 Kelvin. That's my value for T1. What's the new pressure, P2, when the temperature is changed to 336 K? That's T2. And the volume is decreased to 450 milliliters, V2. So I recommend starting out with our combined gas law equation. Now we are solving for P2, so the way you can isolate for that is to divide both sides by V2, which will cancel on the right, and then multiply both sides by T2, which will cancel on the right, and then we have our new reformed equation. P2 is T2 P1 V1 over V2 T1. You can substitute variables now. The second temperature was 336 Kelvin. The first pressure was 2.5 atmospheres, and the first volume was 900. And the second volume was 450, and the first temperature was 298 K. So from here, we just solve. And I got 5.64 atmospheres as my answer, which is perfect because it matches up with 3. All right, a gas occupies a volume of 444 milliliters. So that's my V1 at 273 K, T1, and 79 kilopascals, which is P1. What is the final Kelvin temperature, so that's my value for T2, which I'm looking for, when the volume of the gas is changed to 1880, there's V2, and the pressure is changed to 38.7, so there's P2. So I inserted my combined gas law equation, and I need to solve for T2. Remember, I recommend cross-multiplying in this initial step because that will get the T2 out of the denominator. And now it's going to be really easy to isolate T2 because I just need to divide both sides by P1 and V1. On the left, they cancel, so my final version for the equation is T2 equals P2 V2 T1 over P1 V1. Now we need to substitute. So I got these values after I substituted, and now we just need to solve. And I got 566. This is a temperature, so that's a Kelvin unit. And 3 is the best answer. All right, we're on a roll. Let's do number 6. It says the volume of a gas is 4 liters, so that's going to be my value for V1 at 293 K. There's T1 and constant pressure. So that means that we'll be able to drop pressure out of the equation. For the volume of the gas to become 3 liters, that's going to be my V2 value. The Kelvin temperature must be equal to. So we're looking for T2. So I'll switch to red here, and we are going to be using P1 V1 over T1 is P2 V2 over T2. But we are dropping pressure out of the equation, and we're actually solving for T2. So let's do a cross multiplication to get T2 out of the denominator. And I get V1 times T2 equals V2 times T1. And we are still looking for T2, so you can divide both sides by V1. And then you see T2 is actually V2 T1 over V1. So now we substitute. So V2 is 3. T1 was 293. And V1 is 4. I can see now when I look at the answer choices that they don't actually want an answer, they just want something that's algebraically equivalent to this. And looking at them closely, I think the answer that makes the most sense is choice number 1. All right, number 7. Which graph best represents the pressure-volume relationship for a gas at constant temperature? So one thing I know is that when pressure goes up, volume goes down. And that's called an inverse relationship. And lastly, all inverse relationships have the same general shape for their curve, which is going to look something like that. So 4 is our best answer. All right, number 8. Looks like we're back to gas laws on this one. A gas occupies a volume of 40 milliliters, so there's my V1, at 20 degrees Celsius. I would like to convert this to Kelvin right now, and the way to do that is to add 273 to this value. So instead of 20, I'm going to write 293, which is 20 plus 273, and it's my value for T1. So if the volume is increased to 80 milliliters, it's going to be my V2 at constant pressure, so I'll drop the pressure out. The resulting temperature would be equal to, so that's my T2 value. So here's my equation for combined gas law. And the pressure is dropping out because it was constant throughout this simulation. And we are trying to solve for T2. And as I have said a few times now, the easiest way to handle that is to cross-multiply to remove denominators. So this leaves me with the equation V1 T2 is V2 T1, which will transform further to isolate T2. And you just need to divide both sides by V1 at this point. And you can see that the V1s will cancel on the left. So we just have T2 is V2 T1 over V1, and we can substitute values that we know. The value for V2 was 80, whereas the value for T1 after conversion was 293, and the value for V1 is 40. So we just need to find the answer choice which is algebraically equivalent to 80 by 293 over 40. And the one that I see which is equivalent is this one, because the 293, which sort of stands alone and doesn't appear to be a fraction, you could think of that as a 293 over 1, And then it's more easy to see that it's 293 times 80 over 40, which is what I've written here as well. All right, we're still on a roll. Let's do another. A 3-liter sample of gas, so this is our V1, is at 288 Kelvin, T1, and 1 atmosphere, P1. If the pressure of the gas is increased to 2 atmospheres, so it's P2, and its volume is decreased to 1.5 liters. That's my V2. They want to know the second temperature in Kelvin. All right, so I wrote in our equation, and we're looking for T2. So let's cross multiply these to get T2 out of the denominator. And so we have P1 V1 over T2 is P2 V2 T1. And we are still trying to isolate T2, but the easy thing to do now is that you can just divide both sides by P1 V1, and you'll be ready to solve for T2. So let's substitute in the values that we know. Pressure number 2 was 2 atmospheres, and volume 2 was 1.5. Temperature 1 was 288. Pressure 1 is 1. And volume 1 was 3. So we just need to solve now. So the value I got was 288. The unit would be Kelvin. And that's choice 2. All right, number 10. Which temperature change would cause the volume of a sample of an ideal gas to double when the pressure of the sample remains the same? So while this isn't a pure math question, we can definitely use math to apply what we know. They do say that the pressure remains the same, so I'm going to remove that from our equations. And we just want to know which temperature change would cause the volume of the gas to double. So if I want V2 to come out with double the volume of the original, then that means that T2 also needs to be double. And that's just straight up algebra right there, because the V1 over T1 needs to still be equal to V2 over T2. So if you're doubling the volume, you also must double the temperature. Now, 2 of the answer choices appear to be correct at first. It seems like choice 1 is a doubling of temperature at the same time that choice 3 is a doubling of temperature. But the only answer that's actually correct is 3. And that's because Kelvin, unlike Celsius, is directly proportional to kinetic energy, meaning when you're at a temperature of 0 Kelvin, the kinetic energy of the particles is also 0. That's not true for choice 1, where a temperature of 0 Celsius still has tons of kinetic energy. So the only temperature scale that has a direct relationship between kinetic energy and temperature is the Kelvin scale. All right, 11 is also conceptual. It says, as the temperature of a gas increases at constant pressure, the volume of the gas. I recommend using an equation to think about this one as well. So it says the temperature of the gas is increasing, but the pressure is constant. So let me remove pressure from the equation. And we said that the temperature of the gas increases, so I'll just put an up arrow in front of the T2 to indicate that it's increasing. And they want to know what effect that would have on volume. So since V1 over T1 isn't changing, then we need to keep the ratio the same on the right-hand side as well. So if T2 is increasing, then V2 must also be increasing. And there's our answer. All right, number 12, a graph question. Which graph best shows the relationship between the pressure of a gas and its average kinetic energy at constant volume? All right, I put in my combined gas law equation again. We're going to keep volume constant this time. And we're looking for the relationship between pressure and average kinetic energy. Average kinetic energy is actually just temperature, especially if we use the Kelvin scale. So they're really just looking for the relationship between pressure and temperature. So we can see that since the ratio of P1 over T1 needs to be the same as the ratio of P2 over T2, then any increase in pressure is going to be accompanied by a similar and direct increase in T2. So that means that there's a direct relationship between pressure and temperature. And any increase in temperature that you would see over the course of the change would be accompanied by a proportional increase in pressure. So the only graph that shows this direct relationship correctly is choice 2. All right, last page. The temperature of a 2-liter sample of helium gas. So here's our volume 1 at STP. So this gives us a temperature and a pressure when they say STP. The standard temperature is either going to be 273 Kelvin or, let's see, 0 degrees Celsius. And since this is a gas law question, we have to use Kelvin. So I'm going to say that this is our T1, which is 273 Kelvin. And it's also going to give us our pressure. The standard pressure is 101.3 kilopascals, or it's 1 atmosphere, and we just need to make it match up with the same value for pressure 2. So pressure 2 is in kilopascals, so I'm going to say that pressure 1 is also in kilopascals, and I'm going to use 101.3. So in any case, it says that it has been increased to 27 Celsius. This is my value for T2, but instead of 27 Celsius, I'm going to write it in Kelvin, and that's going to be 273 plus 27. And if I'm doing my math correct, that's 300 Kelvin. And they say the pressure has been decreased to 80 kilopascals, so that's my second pressure. They want to know the new volume, or V2. So here's our standard equation. We're looking for V2, so let's isolate for that now. And my recommendation is to multiply both sides by T2 and divide both sides by P2. On the right-hand side, T2's cancel and P2's cancel. And our new transformed equation would be T2 P1 V1 over P2 T1. And now we just need to plug in what we know. So temperature 2, I decided was 300 Kelvin, and pressure 1 was 101.3 kilopascals. Volume 1 was 2 liters. Pressure 2 is 80 kilopascals, and temperature 1 was 273 Kelvin. So after solving, I got 2.78 liters. And we can use significant figures on this. We should really only be keeping 2 significant figures. So the better answer is probably 2.8 liters. And that matches up with number 3. So 14, it says, as the temperature of a given sample of gas decreases at constant pressure, what happens to the volume? So I wrote in my combined gas law equation. And since the pressure is constant, we can drop it out of the equation. And they want to know what happens when the temperature decreases. So I'll put a down arrow with temperature. And remember that the ratio of V1 over T1 needs to be constant to the ratio of V2 over T2. So if T2 is going down, so also must V2 go down. So that means that your best answer is decrease. Last question. So the pressure on a 200 milliliter sample of CO2, this is my V1, at constant temperature, so we'll get to drop the temperature out of the equation, is increased from 60 to 120. 60 is going to be pressure 1, and 120 is going to be pressure 2. They want to know the new volume, or V2. So start with your combined gas law equation. They mentioned that temperature was constant, so you can drop that out. And we are isolating for V2. So I just recommend dividing both sides by P2 to get V2 alone. So my transformed equation is V2 equals P1 V1 over P2. And we can substitute values. P1 is 60 kilopascals. V1 was 200 milliliters. And P2 is 120 kilopascals. And my value for the answer is 100 milliliters. So that concludes our review of Regents questions for gas laws. And I would just like to say thank you for watching, and I hope that you got some great practice in.